Hello, everyone, and welcome back to the lecture series describing the properties of solutions. As I mentioned earlier, a solution is a homogeneous mixture of two or more substances. The major component is called the solvent, and the minor components are the solutes. A solution consists of solvent and one or more solutes, which are substances dissolved in the solvent. Although many of the most familiar solutions involve a solid dissolved in a liquid, the components of a solution may be solid, liquid, or gas. The possible combinations give rise to 7 distinct types of solutions, which we classify by the original states of the solution components. The table presented here gives an example of each type. In this module, we focus on solutions in which the solvent is a liquid, and the liquid solvent we encounter most often is water. Also, recall that solutions in which water is the solvent are called aqueous solutions. Solutions can also be classified by the amount of solute dissolved relative to the maximum amount that can be dissolved. A saturated solution is one that contains the maximum amount of solute that will dissolve in a solvent at a specific temperature. The amount of solute dissolved in a given volume of a saturated solution is called the solubility of that solute. It is important to realize that solubility refers to a specific solute, a specific solvent, and a specific temperature. For example, the solubility of sodium chloride in water at 20 degrees is 36 grams per 100 milliliters. The solubility of sodium chloride at another temperature or in another solvent would be different. In this respect, as you have probably guessed, an unsaturated solution is one that contains less solute than it has the capacity to dissolve. On the other hand, a supersaturated solution contains more dissolved solute than a saturated solution. Such solutions are typically prepared by dissolving excess solute at elevated temperatures. They are generally not stable, and eventually the dissolved solute will come out of solution, especially if we add a sample of the solute, which can then act as a center for crystallization. We should now take a more general look at the factors that determine solubility. The following discussion will enable you to understand why so many ionic substances are soluble in water, which is a polar solvent, and it will also help you predict the solubility of ionic and molecular compounds in both polar and nonpolar solvents. As you may have anticipated, the intermolecular forces that hold molecules together in liquids and solids play a central role in the solution process. When a solute dissolves in the solvent, molecules of the solute disperse throughout the solvent. They are, in effect, separated from one another, and each solute molecule is surrounded by solvent molecules, a process known as solvation. The ease with which solute molecules are separated from one another and surrounded by solvent molecules depends on the relative strengths of the solute-solute interactions, solvent-solvent interactions, and solute-solvent interactions. Unlike the intermolecular forces that exist within a pure substance, solute-solvent interactions occur in a mixture of different substances. Since the components of a mixture can have different properties, there's a greater variety of intermolecular forces to consider. In addition to dispersion forces which are found between all substances, dipole-dipole forces which exist between polar molecules, and ion-ion forces which operate between ions, solutions can also exhibit ion-dipole interactions, where the charge of an ion is attracted to the partial charge on a polar molecule. We can also have dipole-induced dipole interactions, where the partial charge on a polar molecule induces a temporary partial charge on a neighboring nonpolar molecule or atom. Finally, dissolution can be facilitated by ion-induced dipole forces, in which the charge of an ion induces a temporary partial charge on a neighboring nonpolar molecule or atom. For simplicity, we can imagine the solution process taking place in the 3 distinct steps shown in this figure. The first step is the separation of solute molecules from one another, while the second step is the separation of solvent molecules from one another. Both of these steps require an input of energy to overcome intermolecular attractions, so they are endothermic. In the third step, the solvent and solute molecules mix. This process is usually exothermic because, like the formation of chemical bonds, the formation of intermolecular attractions is exothermic. If that isn't intuitively obvious, think of it this way. It would require energy to separate molecules that are attracted to each other. The reverse process, the combination of molecules that attract each other, would give off an equal amount of energy. The enthalpy change for the overall process can be represented as follows. The overall solution formation process is exothermic when the enthalpy of solution is negative, meaning the energy given off in the third step is greater than the sum of the energy required for the separation of solute and solvent molecules. The overall process can also be endothermic when the enthalpy of solution is positive, meaning the energy given off in the third step is less than the total energy required for the separation of solute and solvent molecules. You have probably heard the saying like dissolves like, which is quite useful in predicting the solubility of a substance in a given solvent. This expression means that two substances with intermolecular forces of similar type and magnitude are likely to be soluble in each other. For example, both methanol and water are polar liquids, and the main intermolecular force between the molecules of pure water and methanol is hydrogen bonding. When these two liquids are mixed, they readily dissolve in each other because the attraction between methanol and water molecules is comparable in magnitude to the forces between molecules in pure methanol and those between molecules in pure water. Two liquids are said to be miscible if they are completely soluble in each other in all proportions. Alcohols such as methanol, ethanol, and propanol are miscible with water because they can form hydrogen bonds with water molecules. However, as the hydrophobic aliphatic chain grows in the succeeding alcohols, dispersion forces become more prominent. As a result, the solubility of higher alcohols in water diminishes, and they become miscible with nonpolar liquids like hexane. Similarly, tetrachloromethane and benzene are nonpolar liquids, and the only intermolecular forces present in these substances are dispersion forces. These two liquids also readily dissolve in each other because the attraction between tetrachloromethane and benzene molecules is comparable in magnitude to the forces between molecules in pure tetrachloromethane and pure benzene. When sodium chloride dissolves in water, the ions are stabilized in solution by hydration, which involves ion-dipole interactions. In general, ionic compounds are much more soluble in polar solvents than in nonpolar solvents. By polar solvents, I practically mean water, liquid ammonia, and liquid hydrogen fluoride. Since the molecules of nonpolar solvents, such as benzene and tetrachloromethane, do not have a dipole moment, they cannot effectively solvate the sodium and chloride ions. You already saw that the predominant intermolecular interaction between ions and nonpolar compounds is an ion-induced dipole interaction, which typically is much weaker than ion-dipole interactions. Consequently, ionic compounds usually have extremely low solubility in nonpolar solvents. Another interesting topic we should discuss is the categorization of vitamins. If you have ever studied biomedical sciences, then you know that vitamins are typically categorized as either water-soluble or fat-soluble. You probably know that an excess of a fat-soluble vitamin can be stored in the body, whereas excesses of most water-soluble vitamins are eliminated in the urine. The difference between water-soluble and fat-soluble vitamins lies in their molecular structures. Water-soluble vitamins, such as vitamin C, have multiple polar groups that can interact with water to form hydrogen bonds. On the other hand, fats are nonpolar molecules containing hydrocarbon chains, and fat-soluble vitamins, such as vitamin A, tend to be more hydrocarbon-like. While they may have a polar group or two, The molecule is predominantly nonpolar. The elimination of vitamin C causes the urine to become more acidic, which can inhibit the growth of some bacteria responsible for urinary tract infections. Therefore, many physicians recommend taking larger doses than the official recommended daily amount of 60 milligrams to lower the incidence of such infections. In contrast, fat-soluble vitamins cannot be eliminated in this way, and taking too much can lead to vitamin toxicity. In discussing solutions, we must be careful to distinguish the physical process of solution formation from chemical reactions that lead to a solution. For example, nickel metal dissolves on contact with an aqueous hydrochloric acid because we get the reaction presented above. In this instance, the resulting solution is not that of the nickel metal, but rather its salt, nickel chloride. If this solution is evaporated to dryness, we obtain hydrated nickel chloride instead of metallic nickel. On the other hand, when sodium chloride is dissolved in water, no chemical reaction occurs. If the solution is evaporated to dryness, sodium chloride is recovered unchanged. Therefore, my focus throughout this module is on solutions from which the solute can be recovered unchanged. To sum up, in this lecture, you have learned that solutions are homogeneous mixtures of two or more substances, which may be solids, liquids, or gases. We have taken a molecular view of the solution process, and you saw that the ease of dissolving a solute in a solvent is governed by intermolecular forces. Energy and the increase in disorder that occurs when molecules of the solute and solvent mix to form a solution are the forces driving the solution process. The following diagram can help you determine the type of intermolecular force that exists between solute and solvent particles. For instance, if ions are involved in dissolution, then you either have ion-dipole or ion-induced dipole interactions in the solvent. If neither the solute nor the solvent is an ionic compound, the situation can be more complex. If the solution process involves only nonpolar molecules, then you should expect only dispersion forces. If one of the components in solution is polar, then you should have dipole-induced dipole interactions. If both the solvent and solute are made of polar molecules, then you have dipole-dipole interactions, a specific case of which is hydrogen bonding involving molecules where hydrogen is bound to either nitrogen, oxygen, or fluorine. In the following lecture, I will introduce you to the colligative properties of solutions. Thank you for your attention.